Welcome to this final video of the Part B Lecture Notebook Solutions to Activities. We will go over the integration over the dartboard activity, which is the final activity before the summary activity that you have to do yourself. So in this activity, I ask you to base your first code on the random disk darts function that is above. I want you to create a new function, my Monte Carlo disk, my MC disk, that estimates the integral of a function f over the unit disk. This function should have as input parameters f and n, where f is the function to be integrated. It should return an estimate of the integral of f over the disk, as well as the other outputs returned by random disk darts. So there's two lines of code needed here. One is average function, and what I mean by two lines is like in addition to what's on random disk darts. So you need to actually compute the average function value, and then you need to then actually take that average function value and compute the integral approximation by scaling it by the approximation of the size of the set A. So let's go ahead and look at random disk darts. Let's go ahead and copy and paste. So, all right, so we're copying it. Now notice this function, the whole purpose of the existence of this function was nothing more than to show how to generate random numbers within a set A, where A in this case was defined as a disk. Inside that was circumscribed by a square. So in this case, what we're saying is we want to actually take those random numbers and then evaluate a function on them, and then use the average value of that function to approximate the integral of the function over that set. That's all the point of my MC disk is. So we'll copy and paste this here because we're basing it on there, and we're going to call it my MC disk. And it should have as parameters f and n. So now you're passing a function f. You're saying how many random numbers to throw at the dartboard, which is the square. So you throw the darts there. Then you determine which of the darts are in or out of the function. You're approximating the area of the disk. I mean, we know this exactly, but I'm just showing you how you can approximate it here. And then, all right. And it's just based on the proportion of the darts that fall in there times the area of the dartboard. And so now all I need to do is, at the end of this, compute the average function value of all, right? So this is the function evaluated at all the darts that have fallen inside of the disk. That's the target of my set. And I'm taking the average value of those, right? Because these are the indices of the darts that fall in that A. And then I need to compute the actual approximate value of the integral. So now what do I say? It should return an estimate of the integral of f over the disk as well as the other outputs. So as usual, we'll create the last output as the integral approximation, so we can just use, like a -1 indexing if we wanted to just get that output of that function. So it should return this approximation. That's it. That's really all I need you to do is you copy the function, you change its name, you add that parameter f, and then these two lines of code and this output. That's all there is to the first part of this activity. And then I ask you to run some tests for different lambda functions of your choosing. You could just go ahead and use the ones we've been doing before. So you might say, hey, I'm going to create f of x equals x function as my first one. And then you could test what the Monte Carlo approximation of that is. Now, the thing is, you could use those. Those original functions are just functions of a single variable, though. And this is the whole point of this, and I'm going to run this this set of code here, is we're talking about integrating a function over a two-dimensional input space. So it should be evaluated at like an x and y, so to speak. It should be like the lambda function should really have maybe two inputs. So in that case, I would say, hey, we should integrate maybe, we'll say x and y, and maybe we do x minus y. All right, so we just take the difference of these. In that case, we have these first and second inputs, and they should be actually valued. Now I'm looking at how we're evaluating the function here. In order to do this properly, if we wanted a lambda function, this is getting an array of two inputs, right? It's getting an array of these things. So I think what you really want to do is you get your x's, and they could be, I'm just going to call it a little bit something different here. And you're going to take the first column, which is the x values, and let's say I want to subtract the second column, which is the y values. So that would be really what you want when you're passing it an array of shape, where it has a length of the rows are the number of points that you're talking about, and the columns is the number of dimensions, and it's 2 columns in this case. So I'm taking the first column as the x value, and the second column as the y value. So that creates a function x minus y. Why do I want to do that? Well, that creates a symmetry. That function x minus y, I kind of know what's going on this disk that's centered at 0. Its center is here at 0. There's a 0 there and a 0 there. And it's going to be like kind of, for a sufficiently large n, I'm expecting values that are around 0. So it's a good way for me to test that this is correct. So with that function, if I go ahead and compute, so let's say I just print out my MC disk, and I do it with this function f, and let's say with n equals, let's do 1e to the 5, and let's say I return, then I just want the last output, which is the integral approximation. This should be near 0. Let's make sure. Hopefully I don't get an error. No error. Okay, 0.006. Okay, that's approximately 0. You could run it a few times. 0.004. 0.002. Yeah, I'm getting things that are nearly 0. I expect that some of them would come out maybe negative. There we go. There's a -1. You could then loop through these and create histograms like things I did before with Monte Carlo approximations, and you would see that this is doing it correctly. I'm integrating a multivariate function, a function of 2 variables, for which I know that the output of the integral, the exact value is 0. But it's a function of 2 variables, so it's a little harder to use in some of the quadrature functions. It's not impossible, but I don't really want to get into it in this recorded lecture, or excuse me, this recorded video of solutions. But this appears to be working correctly. Now, if I was to, similarly, you could do x plus this. That should also be centered at 0, but you could do something, what would be another one? Let's see. This would definitely, if I made it like 2, this needs to return 2 times the area of the disk, right? Well, this is a disk that's centered at 0, radius 1. I know what its area is. It's pi. Pi times r squared, and the r, the radius is 1. It's pi. So 2 times that, or let's say just 1 times that, right? If now I'm just not using the x's at all, it's just a constant function. This should be getting results that are close to 3.14, about the area of A. So let's just check that. 3.135, I'd say that's pretty close to pi. 3.14, yeah, these are close. So this seems to be working. I'll kind of go back to what I had before. You just choose some different ones. You could look up, go to Wolfram Alpha or other resources to look at what integrals of some scalar valued functions, real valued functions of 2 variables are over a disk. If you could figure that out with calculus or some other means, it's okay. You're just really running tests to make sure your code's working. And I just wanted to say, here, I'll make that back a minus. Like there's some values where you could use symmetry arguments to say like, well, the value should be about 0 and make sure that it's working. Now, based on plot random disk starts function, I want you to create, and you just obviously have to do this for at least 2 functions. If I say for different lambda functions of your choosing, you need to do at least 2. You might want to do this one, a different one, constant. It's up to you. I want you to, in this last, second to last part, I'm not going to do the recommended but not required part. I want you to create a plot random disk starts function, based on plot random disk starts, create a plot Monte Carlo disk. And it plots the darts that, and it uses the myMC disk, meaning this function, to approximate the integral of f over the disk, and it plots the disk, the darts that fall in and out of the disk, and then it displays the approximate integral of the function f as the title of the plot, all right, like this output. So the whole point is this. I'm saying, hey, based on this function up here, just copy and paste this one, all right, plot random disk starts. But what you should do is you should rename it, because we're not just plotting the darts anymore. We're interested in the MC approximation of a function. So we're plotting the Monte Carlo approximation. You should be passing a function f, right, along with n as parameters into this function. Otherwise, it doesn't make any sense. And then you need to be grabbing the integral approximation, right, the int f approximation as the output. We're not calling random disk darts. We're calling myMC disk. That's what's in the instructions. So myMC disk. here's f comma n. And then for the title, where instead of saying, hey, we're approximating the measure of this dartboard, is we're going to say that the integral over a of f of x dx is approximately, so this is, there we go, is approximately equal to, and then we put in a number, and we're going to put in, not that, we're going to put an int f approx. And in fact, now we don't really care about this one at all. It's not being used. So if it's not being used, it's best to put like an underscore just to skip over it. Alternatively, you could, here's a fancy way to do it. So that you do this, you could say, I want the 0, 1, 2, and 4. I want those outputs. I'm skipping the third one. I think that one's actually a little bit more complicated, though, than doing this way, where you just say, I'm not using that output. Because if you're returning it and somebody was looking at your code, and they're like, where does that ever get used? It doesn't. Here you're explicitly saying, I know it returns this output. I'm not going to use it, so you just use this to kind of skip over. It's not stored as any variable name. So I can run that. And then I just want you to demonstrate this on some functions of your choosing. So hey, let's do this one, right? And so now I'm going to call, I'll do it non-interactively. You don't have to do it with widgets. So let's just plot MC, plot MC disk. And we'll do the same function f, well here, because you might have done different ones before. Well, let's just go ahead and copy paste that because you should have several ones here. Let's go ahead and, well, in this case, I really just want that part of the function. So let's just go ahead and put that in here like this. F equals lambda. There we go. And let's just go ahead and make, let's say, 1,000 points. And let's plot it. And the approximate integral is about -0.01. There you go. And we see we have all the darts inside, the ones that fill out. And we're integrating the function f that we pass to the function. And we know it should be about 0. And of course, you run it again. And it's positive, right? And, I mean, it's going to be different numbers what you're getting because of the random seeds are all going to be different between what I'm running and what you're running. And if you want to run this multiple times, you could do a run interact, an interact manual like what I did up here. You could do something like this. And you would just have to make sure to call the right function. Do this for a few different functions, show the outputs of it. And if you wanted to say like, hey, what would the integral be for like, if I was doing like x squared plus y? What would that be? It's about 0.93. If I run this a few times, 0.84. Like, what's the actual integral? You run enough points, let's say 10,000. At some point, you just want to like cast these things as integers, 1e to the 5. So there's 100,000 points. It's going to be a dense plot. I would say 0.79 looks like a pretty accurate approximation. That's a really dense plot. Oh my goodness. Look at the amount of memory we're taking up now, 622 megabytes. Yeah, I don't think I want to run much more, but let's just run it again. And about 0.79. So I'd say that's a pretty accurate approximation to what x squared plus y is. What if we do x squared plus y squared? Right? What is that going to be? It's larger, 1.56. Let's run it again just to make sure, about 1.57. So there's a little bit of variation, but we're using so many points, it's pretty accurate. To 2 decimal places, it's pretty stable. About 1.57 seems to be the answer for that. So you can just play around, and this just allows you to be like, man, I could integrate over like a really complicated set for which calculus rules would be a real pain or maybe an impossibility to even get a closed form answer. And you can just use random numbers to approximate the integral. And if you use enough of them and you have a good rule, so you'd have to code up some function that describes how to determine if like the random darts you throw at a board were in or out of the set. But if you threw enough of those simulated darts and evaluated the function and took the average value of those functions and took the proportion of darts that were in the set versus the total number of darts, the proportion of darts that fell in the set times the area of the dartboard, like a big rectangle, you could approximate the integral of almost any function to arbitrary accuracy over any complicated region of integration. It's kind of amazing that you could do that with simply just generating random numbers by simulating throwing darts at a kind of a complicated target. By first generating darts on a simple target like a rectangle, and then just figuring out which darts fell in or out of the complicated kind of bullseye that you've defined. So anyway, just do a few more functions. You can play around with it. And then there's some other things I ask you to do, like for instance, change it from a disc to an ellipse. If you can do that, that's really cool. It's fun to see. And then you start to see how you have, like the main thing you have to change there is this computation. You just look up formulas, like how would I determine whether something's in an ellipse or not? And if something was in a much more complicated shape, you'd have to think like, how do I determine whether or not the darts are in or out? So you could even try changing, think of different types of geometric shapes, or like a triangle, or some other type of maybe more complicated user-defined shape. I used to have an activity that involved a Pac-Man with a mouth opening and closing and an eye. That was kind of a fun one, but it was a little too hard, I think, for students to work through. But it was doable. You can make these things kind of interesting. And you could say estimate the amount of yellow area that was in the Pac-Man as his mouth was closing up and down, and with a white space for an eye as well. So anyway, you can kind of have fun with it and experiment, if you want to. This is a recommended thing to try, at least with an ellipse, and you could go a little nuts with it and try different shapes. I'll leave it up to you. But that's it. Thanks for listening, and I'll talk to you in a future video.